Okay, so let's start. So good afternoon. So I'm referring to the people from Brazil, probably elsewhere, or at least in the North Hemisphere is night. But anyway, welcome to the talk, Scene Understanding with OpenXR by Professor Jürgen Schulze. My name is José Mário de Martino. I'm a professor at the School of Electrical and Computer Engineering at the State University of Campinas, Brazil. I will host the talk together with Elton Cardoso Nascimento, a teaching assistant for the Extended Reality Project graduate course that we are offering this semester at the School of Electrical and Computer Engineering, with the support of Qualcomm. For the record, today is June 2nd. We are in the School of Electrical and Computer Engineering at the State University of Campinas, Brazil. It is 3 p.m. Brasilia time. After the talk, if time permits, we'll hold a question and answer section. We will alternate between questions posed by present and remote participants. The event time limit is 4 p.m. I'd like to start welcoming the audience attending the event. I would also like to thank Adrian Nunes Rocha, Qualcomm University Relations Program Manager, and the Qualcomm team that helped us organize the talk and the XR course. And of course, I'd like to thank Professor Schultz to taking the time to talk to and with us today. Dr. Jürgen Schultz was a software engineer in the XR research group at Qualcomm, and prior to that, a research scientist and adjunct professor at the University of California, San Diego. He has a strong background in developing innovative virtual reality and augmented reality applications, 3D human-computer interaction techniques, and medical data visualization methods. He earned his master's degree from the University of Massachusetts and his PhD from the University of Stuttgart in Germany. He also conducted postdoctoral research on real-time volume render in virtual reality at Brown University Computer Science Department. Currently, he's working on a novel approach to use AI and AR in real estate. Dr. Schultz, thank you, and please welcome.
Thank you, Jose. That's a pleasure. It's a pleasure to be here, and I really appreciate having the opportunity to talk to your class today. I'm going to, I thought, of the many things that I've done in the realm of XR, that scene understanding is one of the more recent ones that I did. I worked on that when I was at Qualcomm, and I'm also still very interested in that now because it's only sort of in the infancy of what it can be capable of, in my opinion, and so it's useful to keep an eye on the developments there and figure out what we can do with those features. So first of all, I want to just briefly introduce what OpenXR is. I'm not sure how far you all got in your class on that topic, or if you even covered it at all, but OpenXR is essentially a programming API that allows an application to run on a variety of different hardware devices. So in the schematic over here, for instance, we have multiple applications. So these can be different games or other applications, whatever people want to use. And they can be built on top of whatever the engine is that they want to use. So it could be Unity, Unreal Engine. Those are probably the biggest ones. But it could be anything really. As long as that engine supports OpenXR, then it can use OpenXR. It has to support it though. And that's where OpenXR comes in. It's sort of the unifier of these engine interfaces. And then what it abstracts from is essentially the API that allows you to access your device. And there are different such APIs. There's, for instance, SteamVR. SteamVR supports a variety of devices, so that can be used as sort of a driver for many headsets. the Oculus API is specifically for the Oculus headsets, and then some manufacturers have their own specific APIs. And then there's the OpenXR device layer, which allows these APIs to access the actual virtual reality headset that people use. So that could be an Oculus Quest, or it could be a Lenovo BRX, or any type of device that has OpenXR support. Benefits of using OpenXR include that you have the ability to support many devices, even if you only have one, let's say, to develop for. But as long as you use OpenXR, there's a good chance that it'll work, or with minimal adaptations, work on other headsets. And that makes it a lot easier for an application developer, so that they don't have to write different code for different headsets, as it was actually the case for a long time before OpenXR came along. And thus it makes application development faster, which is, in the field of XR, is always an issue anyway, is that the market isn't huge. So it's very critical to be able to develop with a lower budget and access as many customers as possible. So OpenXR consists of, or requires rather, a runtime in order to work. And these runtimes are basically high-level drivers that support specific devices. And not all of those that were listed on the previous slide, but it's whatever the runtime was written for. So there's, for instance, a very popular one from Microsoft, the Microsoft OpenXR runtime, and that supports Microsoft devices, especially the HoloLens. And the Microsoft HoloLens came out a while ago, I think about 8 or 9 years ago. So that's been around for a long time. And around that time is when Microsoft started implementing the runtime, and also the OpenXR code for the support of these devices. A system can have multiple runtimes installed, just as you can have multiple drivers for multiple devices. And you would just have to, if you have multiple VR headsets, let's say, with different runtimes, then you have to just have the one be active that you want to use the headset of. And then there's the concept of the OpenXR loader, which figures out what runtime is running on the system, and which, if there's multiple, it would be the active one, and then loads that runtime. So that's the OpenXR loader. That's a term that comes up very often in when you read about OpenXR. And then OpenXR extensions. Extensions are a concept that allows the application to access not only the regular standardized OpenXR commands that are supported by all the runtimes, but it also allows a runtime to support additional functionality that it maybe wants to offer for the application developer because the hardware offers it. And that is something that can be either done in a way that it's an extension that's standardized across multiple vendors, or it could be an extension that only was created by one company, by one vendor, for the specific devices that they build. So there is, for instance, there's a set of OpenXR extensions that Microsoft created. There's a set of OpenXR extensions that Meta created, and these are proprietary, or not proprietary, but they're called single vendor extensions. So that means that they are only supported for devices by that particular vendor. And then there are also, as opposed to single vendor, there's multi-vendor, which would mean that multiple companies teamed up. For instance, there is a new plane extension that just came out last summer that was created by that's an OpenXR extension, but it was created by Qualcomm, by Meta, and also by Magic Leap, working together on an extension. I was actually part of the development of that. So there's multi-vendor extensions, and then what's even more sort of ubiquitous is an extension that's vetted by Kronos. Kronos is the company that created initially OpenGL and now OpenXR, and also Vulkan. They manage the API, and when an extension turns from a single vendor to multi-vendor and is accepted by the community, then Kronos might offer to accept it as a standardized extension. So when you have an OpenXR application, there are typical processes that you have to use to get the application to work and to get everything instantiated. I just wanted to get everybody an idea of what these commands look like and what the general idea is. It doesn't make sense for y'all to fully understand what's going on in the slide, but it could be a good slide if you actually want to dive into OpenXR application development. What's probably the most important part of this slide is on the left. There's this one column of boxes. That's sort of the very high level application flow, where when your application starts, there are some OpenXR commands. They always start with the letters XR. And these commands have to do with figuring out what the OpenXR runtime supports. And then an instance of that OpenXR runtime is created, and then happens the session, which is the actual application that you would develop. And at the end of it, everything gets cleaned up so that the system is ready to run other things. And then you could dive into what a session looks like internally, and then what these there's multiple other commands that have to do with, for instance, figuring out what the headset offers, like how many displays there are, typically 2 for stereo, what these displays look like, what their resolution is, what their aspect ratios are, and all these things, where they're located in the headset so that you can do proper stereo, and all those things that have to do with rendering an OpenXR scene. And it also has to do with access to controllers. For instance, it's not so OpenXR doesn't only specify access to headsets, but also to input methods, and that could be controllers, of which there are a variety of different ones. Meta has its own proprietary controllers. Microsoft developed headsets for a while that came with their own controllers, and there's, of course, there's a whole bunch of other controllers, the Vive controllers, and so on. And also, besides controllers, users might want to use their application with hand tracking. That's been around not quite as long as controllers, but it's getting better and better. And also, there's some headsets have eye tracking, so that you could use your eyes to also play a role in how you interact with the system. For instance, the Apple Vision Pro headset, as you probably all know, has eye tracking built in, so that you can use the eye tracking to select things on the screen and then use your fingers to pinch and trigger actions. So that's all supported. I'm not sure if the Vision Pro actually supports that all. I haven't worked with it in OpenXR, but this functionality is supported in OpenXR, so that when a device wants to write a driver, a runtime for it, then you can use all that functionality. So extensions, we want to talk today about the scene understanding extension specifically. So I wanted to show you how extensions in general work. What we have here is an OpenXR application in which you can imagine that you're writing a function call for, maybe you want to say, get me the button state of controller number 1, right? So maybe if that was a function that was actually maybe using an extension, then this diagram would come in. So you have your function that you call, and this is a regular function call like you would do in any programming language, and that gets executed by the application, and then it gets sent first into the OpenXR loader trampoline. The loader trampoline is a place where in the OpenXR runtime, it looks at all these function calls and figures out who has to actually execute them. Because there could be multiple options. There could be a core functionality that supports this function call, or there could be extensions, and there could be more than one extension. And multiple extensions can actually support the same exact function call, because it could be something, let's say, if the function call is gets the depth map of the screen, right? Then maybe there's multiple threads running, and that are all using different using the depth for different functionality. One could be for hand tracking, or for creating a 3D model of the space. And those could all be different extensions that all want to use that same function call. So you'd have multiple API layers that can support a function or not. And then eventually, and what's also important is that they have to pass through the extension call to the next extension. and they can actually modify it so that so the output of one extension could go into the input of another, which can be useful to override functionality that's defined in a different way. If some of you remember, for instance, there are OpenGL interception libraries that can, when a game runs on OpenGL, you can load an OpenGL driver that's not actually the original driver, but it's a modified driver that, for instance, takes all the functionality that all the OpenGL calls and feeds them into a 3D headset, let's say, so that you could run a 2D game that was written for 2D. You could run it on a 3D headset, or do other things. Save the 3D state of the 3D world into a file or something like that. So these function calls can be modified and overwritten. Of course, there's a mechanism there so that there can't be hostile actors. There's an authentication method that makes sure that these extensions are vetted, and someone can't just come in and run an extension that does things that the application doesn't want to happen. So the calls go through these layers, and eventually they come back out at the runtime and get wrapped up. So scene understanding is one of these extensions where a call gets made by the application, goes to the trampoline, and then there's typically just that one scene understanding library that supports the function call, and then and it could be multiple. I've seen it in cases where ray casting, for instance, you cast a ray into the scene to click on something, and the ray hits multiple things. Maybe it hits a environment mesh, and then maybe it hits a plane, because they're all kind of aligned with each other, so that when you cast that ray into the scene, you hit multiple of these objects, and in that case, it may be that multiple extensions get triggered by the same raycast. So so that's sort of the method for how extension calls are done in the runtime. Now, what does scene understanding mean? What's that for? So scene understanding in general has to do with running an application that's an AR application, augmented reality, rather than virtual reality. Virtual reality applications, they don't need a whole lot of scene understanding because they create the entire scene virtually. You typically play some game, like let's say mini golf, and all the only thing that you really need to know about the environment, the physical environment in front of the user, is if there's an object that's in the way, so that the user would run into it, like a wall or a piece of furniture. So that would be where scene understanding comes in for virtual reality applications. But for augmented reality applications, it can play a much bigger role, because you could have the whole application be set up and interacting with the environment, so that you would want for the scene understanding functionality be available throughout the application. For instance, to throw a ball at a wall, a virtual ball at a physical wall, or something like that. So it's there to capture and interpret the physical environment. It involves detecting surfaces that could be walls, ceilings, floors, but also tables, desks, and such that you might want to put something, a virtual object, on, and also spatial relationships, like what's in front of what, to create a digital model of the real world. So it's sort of a digital twin of the real world that we want to create with scene understanding. So this means that the XR system that runs a scene understanding algorithm tries to understand the layout and the geometry and even the semantics, which means what things are, like whether some object is a table or a dishwasher or a chair, or whatever it could be, because that could play a role for the application programmer if they want to put an object like a laptop onto an object. Maybe they want to make sure that it ends up on a table rather than a dishwasher, right? So the scene understanding enables placement of virtual objects and physical objects, and also interaction with virtual objects that live in this mixed reality of virtual and physical objects. Scene understanding pretty much always supports some type of spatial mapping, so that you can walk around the 3D space and you can use it to place objects, to throw things, or even in industrial applications, it could have to do with detecting machinery that you want to maintain. Or also, I should mention, there's not just industry applications that have to do with machinery, but there could also be many other areas like medical, where you could have XR to support surgeons doing surgery, or it could be all kinds of a large variety of different areas. The scene understanding functionality typically improves awareness for better user experience, and sometimes safety, so that you don't run into things or you fall down a deep hole. And also, scene understanding is often used in order to make the virtual objects in the space look more realistic. So that could have with occlusion, which means something could be in front of something else and that has to be correctly rendered. Could be lighting, where if you have a virtual object in a physical space, you would want it to look like it's really there. So you need to factor in the lighting and the shadows that the real environment would cast on a virtual object. And maybe in physics, if something falls, so that it falls correctly according to physics, bounces into other things correctly, maybe breaks correctly, depending on what you have in mind. Core concepts of scene understanding. Spatial mapping has to do with creating this digital twin, creating the geometry of the environment, which has to do with the walls and the objects and everything in it. Then you want to be able to detect objects and classify them. So that could be furniture, walls, and other things. And the list of things can actually be pretty large. Nowadays, the list is relatively small. Scene understanding in libraries like ARCore or ARKit, which are the APIs that phones use. These are Android and Apple phones, respectively. Those libraries typically only have maybe a dozen or so different objects they can recognize, but larger systems can potentially recognize dozens of different object types in the environment. And environmental awareness has to do with monitoring changes in the environment. So that could be lighting, like let's say you have a virtual environment mapped onto your real room, like where I'm now, for instance. If I had a virtual teacup in front of me, right, then I would see it. But when I turn the lights off at night, for instance, then it shouldn't still be there. It should be dark, right, and maybe be take on whatever rest of light there is in the environment, and look just like all the other objects, pretty dim in the environment. So those are things that have to do with making everything as realistic as possible based on what's going on in the environment. It's actually a really good test for scene understanding libraries. If you have the opportunity to run one somewhere on an augmented reality headset, be in a classroom, let's say, and turn the light off and see how quickly the light adjusts. The lighting on the virtual objects adjusts to the physical lighting. Sometimes there's a delay because the system doesn't want to accidentally turn the light off on its objects, and some systems are very, very fast. So this particular implementation of the Microsoft Scene Understanding extension is what I want to focus on today. This has to do with the fact that that's the only scene understanding API that's available currently, and it was created by Microsoft and made available to everyone. And there are implementations for different runtimes, but the API is always the same. For instance, Qualcomm has a runtime that supports the scene understanding API, as well as Microsoft has its own runtime, and I believe Meta does, but Meta doesn't really publish these things as much. So the this vendor-specific OpenXR extension supports things like detection and classification of objects, and there's a limited amount of different classification types it supports. It's basically just floors, wall, ceilings, and what they call platforms, which are essentially horizontal surfaces. It supports spatial mapping. That means the 3D meshing, so it creates a 3D triangle mesh of the environment that the cameras have seen. It allows object recognition, and it gives you, as a developer, access to all of that. It gives you access to the 3D mesh of the environment. It gives you access to the classification of all the objects that it was able to recognize. And it does this through this standardized API that's relatively easy to use, so that you could write a scene graph application scene understanding, sorry, application once and then run it on different OpenXR runtimes. So core components of the Microsoft extension are that it supports sensor input, which comes from depth cameras and IMUs. IMUs are accelerators, accelerometers, and gyroscopes that give you orientation and velocity of the headset, and sometimes controllers. It does its own processing of the scene. So when the headset, let's say, looks around, has its two cameras, it looks at something. Some headsets have a dedicated depth camera, others use stereo for that, but they all create a 3D representation of the space. And then they use that 3D representation of the space to detect planes in it, for instance. Those are horizontal flat surfaces or vertical. And also that's where the object classification happens. So there's some mechanism that figures out what type of objects there are. And this could be as sophisticated as machine learning with some really sophisticated CNN, convolutional neural network that was trained to recognize certain objects. It doesn't have to, it could use other methods to recognize objects, but it could be a CNN. So there could be a lot of compute in what goes into scene understanding on the side of the hardware. And then together, all of these sensors and all these algorithms, they create that spatial model of the environment. And this all happens in real time. It actually even continues to happen. So there's an interesting distinction between, for instance, the HoloLens from Microsoft. It keeps adding to the space. So when you look at your room, it'll create a 3D map of that, of what it sees in front of you, and then you turn your head and it adds triangles to that representation. When something changes, somebody moves a chair, for instance, then over time it'll update the mesh accordingly. So it constantly runs in the background and updates this mesh. But then there's also other approaches, like for instance, the Meta approach, which is for Meta, with the Quest headsets, it's very important to have most of the compute power available for the games that people want to play. So, so even if it's an augmented reality game, what they do is they have you scan the space before you even run the game. So you walk around the space that you're in, the room that you're in, look at it from different angles until the scene understanding unit is happy, and then it tells you that now you can go and play the game. And then it uses whatever it scanned in, and that's it. It doesn't modify that anymore until you choose to update that. So as part of scene understanding, plane detection is one of the more important features that the scene understanding API supports. We covered flat surfaces that it finds. And what can these be used for? They can be used for anchoring virtual objects. So what that means, anchoring, is that it may be that you want to have a window. Let's say you have a YouTube window running, and you want this YouTube window not just float in front of you. You want it to be attached to the wall, and you want it to stay there. As you walk around your house, you might want that YouTube video to stay on that particular wall like it's a TV. And when you turn off the headset and you come back the next day, you want to find that YouTube video there. That would be called anchoring. You're anchoring a virtual object in the physical space, anchored to a physical object like a wall, in order to find it there again. So anchoring is an important feature of planes. These planes, they can be horizontal surfaces or vertical surfaces. Typically, that's all that's needed, because most surfaces that application programmers tend to use are one of these two types. But the extension also provides the ability to detect surfaces that are not horizontal or vertical. So that could be at an angle. And because it could actually be objects that are at an angle in your space. And some implementations will support at an angle. So with these planes, that allows the application to understand the real world better, because if you all you get is a 3D mesh of the environment, 3D meshes are usually very rough. They're not super exact and precise. And they also, even if there's a horizontal surface, the mesh will probably still have, due to tracking errors and image camera recognition errors, the surface won't be perfectly smooth. So the plane detection algorithm fixes that by delivering actual planes. And that's typically used to place objects in the environment. The types of planes are detected are floors, which are detected by finding a horizontal surface that's below the user's head, and that's at about the height of a user's height. And if it finds a surface there, then it calls it a floor. It's often also the triangles in the environment mesh that are the farthest away from the camera and are horizontal and low and below the user. If the system finds triangles in the environment mesh that are above the user and horizontal, then those are typically classified as walls. No, as ceilings. Sorry, I skipped one. Those are ceilings. So ceilings would be horizontal but above the user. And then finally, whatever is a vertical surface, that will be classified as a wall. So that's the simplest way of doing object classification for planes, and that's what is done for these planes. Some implementations like the Microsoft runtime actually also supports platforms, which are horizontal surfaces that are between the ceiling and the floor, and could be surfaces that are tables, desks. They could be counters and things like that. What does the plane detection unit provide? It provides you with a very simplistic representation of the plane. So it gives you a plane equation essentially, which has a normal vector, which is a vector that points away from the surface of the plane, and it has two vectors that are in the plane, so that you can represent this plane, if you wanted to, even just as a very simple flat surface that is infinitely large in your application, if that's all you need. But you can also go in and get the boundary values, the boundary polygon of the plane, which gives you points around the edge of the plane, so that you have constraints for the plane. So if it's a table, the table is not going to be just infinitely large, but it's going to be a specific size, so that you know how big objects can be that fit on that table. So things, this information then could be sufficient to bounce virtual walls off of walls, balls off of walls, and the floor. So you can maybe bounce a ball. And it's better to use planes for that than the 3D mesh, especially when you hit a wall or a floor, because the floors and walls are more smooth when they're defined as a plane, rather than the triangle mesh. It could also, these planes could help, for instance, to figure out, let's say the user wants to place something, the application can ask, show me all the planes that are at a height of about 3 feet, which means maybe, something that you can put something on, like a table. Or what you might want to do is you might want to sort through all of your planes and find those that are vertical and are close to you. So that could be like, where's the nearest wall to hang a picture on it, or a YouTube video. Use cases for planes could be in AR navigation, where you would want to either walk around outside. That would be kind of advanced. Typically, air navigation would be indoors currently, because not all headsets work great outside, and they're kind of a safety issue potentially. But down the road, you would definitely want to be able to take your AR headset outside and have the headset project navigation information, for instance, onto the environment that shows you which direction you have to go, without having to look at your phone and the Google map. Object placement, we kind of covered that already. Environment interaction would have to do with games, where I've seen cool games where you, for instance, can build like a track for cars. If you've ever had one of these like Matchbox cars that run on their track, where you put the track like upstairs, or you put it from a table to the floor. As a kid, I have kids and they love playing with that. And there's actually an app that can do this in augmented reality. So you can use your actual room and put virtual tracks in it, and have virtual cars go along. And I think you can even do roller coaster type stuff, where the roller coaster cars get transported up an incline, and then they go around your entire space wherever you put the roller coaster, and that could be pretty fun, and that requires scene understanding. Spatial mapping is the other big feature that Scene Understanding supports, and I have a little video here. Let's see if this works. We don't need the audio, but this is a video where the user is holding up their device, and you can see the 3D mesh getting built and getting added to as you move your device around. So this is the typical way that these devices do it. That can be the HoloLens, that can be the Meta Quest, or the Snapdragon supported, Spaces supported systems. They all can do something similar to this, or the Vision Pro, they all can do something similar to this. And here, for instance, you could see that the user was filling in a hole in the mesh where they didn't see stuff initially, but then they walked around and eventually saw that and filled that hole. So this is, I thought that was a neat video demonstrating how you can scan a room in. And then if you do this for your entire house or apartments, then you can come up with something like in the picture on the bottom right, where the user walked around and created a 3D mesh with colors, with textures and colors of their entire space. That can be super useful to for real estate, if you want to show someone, if you want to sell your house or something or rent it out, or show them what the floor plan looks like. Or it can be useful just for fun things where you have aliens enter the room, enter one of the rooms and come through doors or whatever. The sky's the limit in what you can do with that idea, right? So this is spatial mapping. And then what sometimes comes along with spatial mapping is that, like in the previous slide, you saw this picture of the apartment that somebody scanned in. So that would be a colored mesh that's colored by the colors of what the objects really are. But when you bring in your machine learning network that segments these objects and finds out what type of thing they are, then you can support things like couches and chairs and tables and walls. But also, if you're outside, you can support things like sky, building, tree, road, vehicle, and so on. And this is where the more spaces some API supports, the more of these semantic segmentation object types will exist. So I imagine that this description of scenes, especially now looking at the capabilities of our LLMs like ChatGPT and things, they can recognize a whole lot of different things, almost everything that we can distinguish as people. And so the coding of these object types is undoubtedly going to go up rapidly over the next few years, and you might be able to distinguish hundreds, if not thousands, of different objects. And maybe there will even be a hierarchy of objects, like, you know, all these seating objects could be classified as something something people sit on, right? But then you would distinguish between chairs and office chairs and lounge chairs and couches and bean bags, you know, all these things. It would be kind of a tree structure where you would have like a general type of object and then more precise description of what that actually is. So I have no doubt that that's going to be added to these extensions over the next few years. Here I have a little video that shows an outdoor application where you're actually using these outdoor object types, and it's rather short, but you can see in colors coded, you can see cars, you can see the road, you can see trees, and that's about the level of accuracy that you can get in real time today with a classification engine that runs on a mobile device. The quality that you see here in the picture with the room, that's also kind of feasible with mobile devices, but it's kind of at the edge of what it's capable of doing accurately enough, because that also requires a relatively fine-grained 3D mesh to work properly. Challenges and limitations of these techniques. There's sort of limited accuracy when you have a complex or dynamic environment with lots of objects around. So, you know, sometimes my office is a little cluttered when I had lots of things going on and no time to clean up. And then my desk, for instance, right now is pretty cluttered, and I don't even know if my Scene Understanding API would actually be able to recognize it as a desk because it's covered by so many things. So, that could be a challenge. There could be a challenge in differentiating between types of things that are similar. Like a problem that we sometimes have is that in this field is that you have a table, and then maybe there's a piece of paper on it, just a like an agenda, right? Like in our meeting today, you guys might have an agenda in front of you, and the agenda is just doesn't really have any 3D shape, right? It just sits on the table. The table is just as flat as it was before and smooth, but there's a piece of paper on there. And recognizing that by these algorithms is not easy. They often just use the depth information primarily, and then they would just see a table. Or maybe if they focus on object recognition, then maybe they would think there's a hole in the table and that's replaced by a piece of paper. So that can be tricky. There can be latency issues. That means that things take a while, especially this object detection doesn't happen super fast sometimes because you have to run your machine learning network, and especially mobile systems, they have issues with power consumption. Always, the battery always doesn't last long enough. So you might have methods that throttle the some of the parts of this algorithm to leave enough compute power for the rest of the application, but then that could cause delays in how quickly objects are recognized, or even how quickly changes are recognized. And especially like this previous video where someone is walking along the street, that's a constantly moving scene. That's especially difficult where latency issues could play a role. Lighting changes can be a problem when it gets darker and it gets harder for the cameras to pick up a good image. And especially reflective surfaces, which could be mirrors. Mirrors are horrible to detect with scene understanding methods because it's so hard in software to figure out if something's a mirror and it just reflects the scene, or if there's actually another scene in that, in the mirror that's right there. Because even depth recognition doesn't help. That depth from stereo at least doesn't help with that, and even some light-based depth cameras don't really figure out a mirror as a mirror either. So that can be very difficult, and it doesn't have to be mirrors. It could be metallic objects of any kind. It could be water surfaces that reflect light. They can all cause big issues. TVs with the glass surfaces in front of them are often an issue for indoor scans. So those are all challenges. Limited support for non-flat, curved, or non-convex surfaces can be an issue. If you have walls that are curved, then they may not be recognized as walls because they're not flat. And then detection range and resolution can be a problem. Like how far does your depth camera actually see? What's the resolution of your pixel map and your depth map? That determines what the resolution of the environment map is that you can create from a certain distance. And another issue is depth detection. So here you can see two videos where that doesn't quite work out perfectly. So in the first video, there's a Pokeball that should be in front of the Pokemon that's in the background there. The Pokemon's supposed to stand on the ground, but because the depth isn't recognized correctly and not acted upon correctly, the Pokeball does not occlude the Pokemon, which creates this weird effect where the Pokemon seems to at first to be in the distance, but then when the Pokeball is in front of it, it seems like the Pokemon's actually closer than the Pokeball, and it doesn't make sense. So that's an ambiguity that gets created. And also in the right video, this Pokemon sits on the table, and you kind of think it jumps off of the table, which it does, but the table should really occlude the Pokemon as it falls down to the ground, but it doesn't because the occlusion isn't detected correctly. So it's really tricky to, especially for moving objects, to detect the depth accurately for every single image in the sequence of images in this video in real time, and that'll probably remain a bit of a challenge for some time to come. In summary, OpenXR provides a unified API for cross-platform XR development. It's very useful for that. It's ready for prime time. The implementations of those runtimes are stable. They offer a lot of functionality. Initially, many years ago, OpenXR was really buggy and problematic, but if you've used it back then and given up on it, look at it again. It's worth it. It works. You can do planes detection, 3D mesh detection, spatial mapping, object classification. You can get updated information when the scene updates. You can get interaction with planes in real time, and ongoing research that happens in the research community and research divisions of companies works especially on improving the accuracy of what's being detected. That has to do with the resolution of the tracking cameras and the depth cameras and such, and also the latency, and especially this discrepancy, the sort of the balance that you try to strike between latency and power consumption. Because for mobile systems, power consumption is so important to keep that low that these libraries often have trade-offs. And sometimes these trade-offs are actually accessible by the developer of the application. So the developer could, for instance, say, well, for me, it's really important that I get real-time updates of my 3D mesh, and I don't care if I have less time to render. Or some other application developer wants exactly the opposite. And some implementations are already offering these trade-offs to be controlled by the application. Some don't yet, but I'm pretty sure that's going to become more and more commonplace, and that you, as a developer, you have more control over that. So yeah, so that's pretty much it. I just wanted to give you a couple of links if you are now interested in exploring this more. There's a OpenXR tutorial for the scene understanding app, for the scene understanding extension, that's by Microsoft. And if you want to read up on the actual SDK, so exactly what it supports and the function calls and such, this is where you would find that for the implementation of scene understanding for Unity, which is likely what you're probably going to be using for AR development in most cases. So this concludes my presentation, and I'm open to answer questions.
Thank you, Jürgen. Thank you very much. So let's start the question and answer session. Wants to pose a question, please? Oh, we have one. You have the microphone, please use it.
Tá funcionando? So you comment that OpenXR makes a digital twin of the real scene. So can we expect to be able to test a virtual robot or agent in a real environment with this? Like it reacts to the real environment, but is virtual. So we can validate logics, but not need to have the hardware.
Yeah, you like simulate a robot in a real environment. So what I'm taking from your question is that you are thinking of creating a virtual robot that would interact with the real environment that the user sees through their headset, so that you don't have to actually build the robots, but you can program it. Is that what you're talking about?
Yes.
Great.
Perfect.
And what's your question?
So could we also input CNNs to detect the relevant objects to this instance using OpenXR?
Oh yeah, would it use CNN? So yeah, so the so what happens? So the CNNs are definitely used by by a lot of scene understanding implementations, where the CNN would be used to classify objects mostly for depth. For the creation of the digital twin, for just the mesh, the 3D mesh, the 3D shape of it, you can use CNNs, but you can also do that with just stereo cameras. So CNNs are optional for that. But when you actually want to recognize objects that the robot encounters, then you will probably need to use some sort of a CNN to detect these objects. Now, an issue with a virtual robot would be that the information about what it can see would come from the user's camera, right? So if you have a headset on, you see the robot in front of you, and the robot roams around the space, it wouldn't, since it's virtual, it wouldn't be able to see things that the user cannot see, right? Like let's say it disappears behind the table. then it may not have information about what's behind that table if the user did not go there yet. So the digital twin would be missing information in the area that the virtual robot wants to go, right? But you could probably solve that by walking around the space ahead of time, create a really good 3D representation, digital twin of the environment, and then let the robot operate in that environment, and that would work really well.
Okay, thanks.
Mm-hmm.
Hello, can you hear me?
Hello, yes, I can. Uh-huh.
Okay, so
How are you?
I'm fine, and you?
Good.
First of all, I'd like to thank you for your presentation, Schultz. It was really enlightening. So my question is regarding, let's say I were to use OpenXR in other engineering fields beyond gaming, let's say agriculture or maybe self-driving cars. What do you think are the limitations of OpenXR in open fields, like outdoors?
Right.
Say,
It's actually it's a really good question, because the original Scene Understanding API was really written with indoor spaces in mind. And I want to say even probably with just one room in mind, that you're in some room in one room, you're not walking around too much. If anything, maybe an entire house that someone lives in, a few different rooms, but not much more than that in terms of space that's covered. A big issue is a few different things. So one thing is storage. When you create a 3D mesh of the environment you're in, and you keep adding to that as you walk around, you just need more and more memory, and that memory at some point is going to run out. And so the question becomes, how does the application deal with that? It could either say, well, I'm running out of memory. Feel free to walk around more, but the mesh is going to stop developing. This is it. This is all I can store, right? That may work, but it's probably smarter to do something where you would discard older parts of the mesh and add the new ones, so that as you reach the limit of your memory, you would say, whatever I haven't used in a very long time, or the parts of the space that I've used less, right? Like, let's say you walk around between two rooms, and there's a corridor in between. Maybe the corridor is less important, but those two rooms are. So in that case, you would want to discard whatever has not been used as much, where you haven't spent as much time. But now we're still indoors, and your question was about outdoors. So the current runtimes typically do Scene Understanding where you're really going to run into problems if you want to have sort of city scale or campus scale. Like, I always dreamt of, when I was at UCSD, to have the ability to scan in the entire campus and walk around and get sort of another layer of information about the campus, like where classrooms are and where stores are and bathrooms and all that those kinds of things. But that was limited by the amount that we were able to do in terms of creating that 3D environment at the time. I think now it might be better with other options like cloud storage and things. But the Scene Understanding extensions typically don't support that yet. So I just have to say that, because that's what it is. Now, will that change? I certainly hope that it'll change, that you could use Scene Understanding in an entire campus or in an entire city. But there are also issues that go beyond just storing the meshes. There's issues, for instance, around even for the headset to create a coherent mesh of the environment as you walk around, because if you constantly walk, that makes it harder for the tracking engine to really know where you are. And then you get drift, which means that the system thinks you are somewhere different than you actually are, and your 3D environment does not represent reality as well. And that's an issue that with drift in outdoor applications, that is definitely currently an issue people are working on. but there's no great solution yet that would work in a large environment very accurately. And much of that has to do with the fact that when your cameras constantly move in one direction, they don't have time to build that map around you as a user and use that then to anchor additional polygons to. But it constantly has to do that with new data, and that makes it hard. A benefit of outdoor applications is that you can use GPS, which doesn't really work indoors as much, especially at the scale of accuracy you need. So with GPS, you can resolve some of these drift issues. Compass information can be more useful outside too. And so there are ways to work around that, and I'm convinced that eventually we'll be able to sort that out. I've even seen applications that don't even create their own 3D mesh of everything, but they use public databases like Google Street View or their own custom databases to recognize places that the user goes to by using cloud algorithms. So you would feed, it's much like when you feed an image into an LLM and you ask it where you are, right, or where that picture was taken. These LLMs have gotten really good at that. And in a similar way, you could feed an image in from your camera that gets compared to a Street View image or to the entire Street View database. If a match is found, then it could figure out pretty accurately where you're located. So I think the outdoor applications probably go more towards that you don't create your entire mesh on your device, but you use a different algorithm, and whether or not that's going to be covered under scene understandings up for debate. I think probably not. I think scene understanding will probably be used more for more confined spaces, like indoor spaces especially. And then there's a different category of algorithms that are going to be covering the outdoors. Yeah, but there's issues in storage, in accuracy of tracking, and also the processing of all of this new data that would be very taxing for a mobile device that runs off a battery nowadays. Is that helpful?
Yeah, thank you.
Mm-hmm.
Hello. Okay.
Hello.
Hey, Professor, thanks for your presentation. So as far as I understood, the information processing of the scene understanding is done inside of the XR devices, right? Okay, so
Right.
in that case, have you thought about like offloading the tasks with another device like a PC with more capabilities? Just for instance, using a 5G or beyond network connection, maybe?
Yeah, so it's certainly a possibility. So the environments I worked with scene understanding in didn't have that as an option, so I haven't actually looked into it. But I know that there's research being done that uses cloud systems, especially edge systems, to do something like this. So an issue with creating these environments quickly, especially if you have an application that really wants the result pretty rapidly, could be that the latency of using a cloud system could be too large. And also the data throughput that it offers could be too large, because you would have to feed it all kinds of images. In these algorithms, they usually take in multiple images of the environment per second, and also the depth map, if it generates a depth map, multiple of those per second. And then they get back a 3D mesh. So both can be relatively large amounts of data that transferring those to a mobile device to a server and back adds more energy consumption, which is why currently these headsets try to do the work locally so that they don't have to deal with that. But when it comes to things like, for instance, for the HoloLens, and this is not part of the scene understanding extension, but there are other extensions that support spatial anchors that can be shared between different people. So let's say, for instance, we're looking still at the slide. I don't know if you still see it, but there are these 5 people that are all looking through their headsets at a virtual scene, right? And presumably there's a there's a virtual object somewhere there. This is obviously AI generated. There's all kinds of problems with this picture, but they could be looking at a virtual image of maybe a Pokemon that they all see in the same place, right? So in that case, all of these headsets would have to connect to the cloud and have a shared scene that's stored in the cloud where the Pokemon is managed, and then the Pokemon would be shown to each user in the right place. So they could basically use their hand and their fingers and point at the Pokemon, and they all would see it in the same place. So that would require some sort of a cloud system. And there are efforts to make that possible, especially with the desire to create multi-user applications that are not just a game that you play, together with others, but really where you have an AR application that shows you an object in front of you that your friends can also see. Because currently AR and VR are pretty sort of single user applications. You can go multi-user over the net, but if you have multiple people in the same room, they don't really work very well. Even two people playing Beat Saber in the same room in VR, if you know that game and have played it, it's very difficult to do that because they move a lot, they can hit each other accidentally, and you can't see where the other person is because you're wearing a VR headset. So for those applications, what you're saying is necessary. And there's definitely early implementations of sharing these kinds of locations in a limited space through cloud methods. But they don't scale very well yet. They scale only to a few users. What I'd really like to see is something like a massively multiplayer game where you can walk through a city and you can see the Pokemon, and everybody who comes by with their headset, they all see the Pokemon in the same place, and there could be hundreds of people. Or concert that someone gives in a augmented reality fashion, right? You've got 1,000 people in the same stadium watching a virtual reality show, right, through their headsets, but they're all physically in the same space. So those kinds of applications, they're not possible just yet. They require too much in terms of data transfer and in terms of compute power, much more than mobile systems can currently offer.
Thank you so much.
Mm-hmm.
Hi, we have a question from the YouTube. So, considering that scene understanding faces challenges with covered walls, how does it deal with objects with miscellaneous shapes, and how can it deal with dynamic objects?
So objects of different shapes and dynamic objects. So objects. So when it comes to object recognition and segmentation, when objects have different shapes, that can happen even just different views, right, of an object. Like you see your chair from a different angle, then it already looks different. In different lighting, it looks different. There's different types of chairs, and recognizing them all as chairs is a challenge, and that's why typically researchers use CNNs for that. They train the network specifically with the objects they want to be able to recognize, and then depending on how well the training works, the outcome will be better or worse, right? So the different shaped objects is a challenge. It's not super accurate. Sometimes you have a chair in your space and it gets recognized as a table, right, or something silly like that. And there's a lot of errors that occur, and one of the measures of quality for these libraries is how accurately they can recognize different objects of the same type that have different shapes, different sizes, and they can still recognize them correctly. So that's one thing. And then dynamic objects are even more difficult because they would be moving around or even changing their shape, right? Like what could be an object? So people change their shape. They move their hands and arms around. They move their legs. Pets are people and animals are actually among the more important things that people want to recognize because they move through a lot of people's spaces. Many people have pets, cats and dogs, and all kinds of pets, and they have family members that could show up in front of their cameras, and almost everybody who creates AR applications wants to be able to recognize reliably what they're looking at. They don't need to know whether that's a man or a woman, but at least knowing whether it's a person or a pet would be useful, because then you can respond to that, and do things like occlusion rendering correctly and do safety algorithms where you avoid them, to not walk into them or whack them with your hand. So that's tricky, and these networks, they just have to be trained. Like if you want to do people recognition with a CNN, you have to train it on many different videos of people in all different poses and from all kinds of different angles. That's just how it has to be done, and that's very tedious to create the training material, and takes a long time to train these networks. And then you have to be mindful of, for these mobile devices, you can't, like OpenAI, they use billions of dollars to train their humongous networks, right, for these LLMs. But for our mobile devices, we only have a very, very small fraction of that capability in the device, so that our networks also have to be much, much simpler. So it's even the training of the networks, it has to be done very consciously to figure out what training material should go into it, so that you focus on the important things that the network is supposed to recognize, rather than trying to recognize everything, right? So when you have dynamic objects that either move around or they can change their shapes, then you would have to figure out where you draw the line as to what you want to be able to recognize and what you don't probably encounter much. Does that answer your question?
Yes, thank you.
Great.
Hi, teacher.
Mhm.
I'm curious about one thing. In the presentation, you mentioned that OpenXR supports depth estimation. So I assume that MetaQuest 3 use infrared cameras. Based on that, do you think it's possible to implement some form of night vision on Quest 3? Is that?
It's a really good question. Yeah, so it does actually use infrared operating depth cameras to measure the distance of objects from the camera. And so I've heard that people actually had success. So first of all, if you take a Quest 3 and you're in a room, it's nighttime, and you turn the light off, Quest is not going to track anymore. It's going to complain. It's going to say it doesn't have enough light to do the tracking, right? But that's not because the depth camera doesn't work, but it's because the other tracking cameras, they need light in order to see. And what you can do is you can provide infrared light for those cameras to do the tracking correctly. So people have put on their headsets, they've actually installed infrared flashlights that illuminate the space around them in infrared light, which the user can't see. And people can't see that. But then the tracking cameras can work again, and the depth cameras, they should probably work without the infrared booster anyway. So you would be able to do night vision. But without, I haven't seen anyone be able to access that depth camera in a way to actually get the depth image out in a low light scenario, because the system will just complain that the tracking doesn't work anymore. And the tracking is really important for the depth images to be correctly correlated to one another, and that's why that probably doesn't work. But if you put an infrared light emitter onto your headset, then you can do night vision today.
Thanks.
Mm-hmm.
Hello, can you hear me?
Yes, I can.
Okay. So I've been thinking about the previous questions about the multiplayer scenario, and I was thinking one step back. I would like to ask about if we have the technology yet to do like persistent things in the world. So, because I imagine that in the single player scenario, I am in an application and I can detect a surface. Let's say I anchor something in a wall and I move around. I expect this to work because I can track the delta of my movements and still kind of know where this should be. But let's say I turn off my headset, I go somewhere else, turn on back there, go back to my house, and let's say I go back to my application and I want to see the same thing that anchored in the same space. Do we have support for this? I expect this to be on the application level of things, but is it possible to do? I'm not sure.
Yeah, yeah. So it is actually possible in many implementations of the scene understanding library. There's if you create a spatial anchor, which isn't part of the scene understanding extension, there's a separate extension for that, but it falls kind of under the same umbrella. So if you load the spatial anchor extension, you can do this, but not necessarily with all implementations. I do know that the Microsoft implementation of spatial anchors, as they implemented for the HoloLens, does support that. So you can use the HoloLens, you can place an object on your desk or on a wall. You turn off the HoloLens, you leave it in a drawer for a week, right, and turn it back on. That anchor will still show up in that same place. You can have many anchors. In fact, you can place a lot of virtual objects in your space. You can even go to other spaces and then later come back to that initial space and they'll still be in the same place. It works really well. One thing that would be interesting maybe to know for you is that the spatial anchors don't necessarily require the digital twin. They don't require the 3D mesh of the environments, because spatial anchors are often implemented in a way that they take the camera images from the area that you placed the anchor in, and they find feature points. They find special points that are unique to that space, and they find hundreds of them. And they sort of create a fingerprint for that location that you place this anchor in. And they store the fingerprint, but they don't store the entire 3D map. They don't have to store the 3D map that the anchor was created in. They just need that fingerprint. And that way you can have many of these anchors. You can even save them to disk if the API allows it, and load them up to another headset. And then that other headset could find that anchor in the space when the camera images pick up these particular unique features, these feature points, when the user goes to that same place. So that works today, maybe not with all implementations, but with many of the implementations that works, and you would use the spatial anchors extension for that.
Oh, cool. That's exactly what I wanted to understand. So it's not position based; it's image feature based, right? So
Yes.
makes sense. Thanks for the answer. Clarified a lot.
Mm-hmm.
Hello?
Hello.
So the OpenXR API is not a rendering API, right? The rendering is separated from the OpenXR.
So you come across very faint. Is it possible that you could get closer to the microphone?
Oh, sorry.
No problem.
I have a question about the API. If the OpenXR is not a rendering API, right? The rendering is, we can use another API like Vulkan and OpenGL, right?
Yeah, the rendering is done by a different, the actual rendering would be done by a different API, but the OpenXR API provides the context for the rendering. So it will create an empty canvas, right? Like a space that you can render into, because only OpenXR knows how many screens there are and how many pixels they have. But then you will have an engine, like you said, like Unity and Unreal Engine, or just OpenGL, however you want to do it, or Vulkan. And you use that empty canvas and you draw your images into that canvas, and then OpenXR will show it to the user. So that's how it's done internally.
Oh, okay. Thanks.
So yeah, so it's not a rendering engine. And you can, for instance, do, you can mix OpenXR and OpenGL, right? Then you would be able to render with OpenGL and you don't need Unity or Unreal for it. And you do the rest of the OpenXR functionality with that library. And then you would set everything up in OpenXR. You would create an image for the left eye and an image for the right eye. And then you would pass on the rendering to OpenGL and tell it, now is your time. Here's the rectangle that you can render into. And then OpenGL would render all of its scene, and then it would say, tell OpenXR, now I'm done. Please show this to the user, right? And then it would show that to the user.
Oh, okay. Thanks.
Mm-hmm.
Again, we pass 15 minutes for our limit, but it was interesting. So I have to close our section, and I really want to thank you very much for your presentation. It was very interesting. All my students here, well, I see they are wanting to ask many other questions, but unfortunately I have to close the session. But I still want to say thank you, and I believe I will send you the, let's say, the partial reports of the projects they are doing. Maybe you can say some words and give some feedback. And at the end of the semester, it means end of June, if you can help me to grade the students, or to at least to give a feedback from the final version of the project, I will be very thankful.
Sure, that'd be great. I'd love to do that.
Okay, Jürgen, thank you very much.
Yeah, Jose, thank you very much for having me. It was a great pleasure, and I'm really glad to see that your students got really interested in the topic, and the questions they asked were really deep, and I could tell they thought about it.
Thank you very much. So I write to you, and then we'll go see how we go continue. Okay. Bye then.
Awesome.
Thank you very much.
Bye-bye. Thank you.